Hello there, and welcome. It's good that you found your way here tonight. Before we settle in, take a second to tap subscribe and like so that this kind of calm, steady explanation can find you again whenever you need it. People who enjoy drifting off to these slow walks through everyday things usually do, and it makes their nights a little easier. Now just let yourself get comfortable. Let your body sink in and your mind slow down. Everything else is taken care of. Tonight we're going to explore something familiar and almost invisible in everyday life: how a washing machine actually cleans your clothes. Ordinary on the outside, but under the surface it's a quiet mix of water, chemistry, motion, and engineering working in perfect sequence. Think about it for a moment. You place dirty clothes into a metal drum, you add some detergent, you press a button, and somehow, almost magically, an hour or so later, those clothes emerge clean. But there's no magic involved. What happens inside that machine is a precisely timed sequence of events, each one building on the last, each component working with the others in perfect harmony. Water flows, temperature rises, drums turn, chemistry happens, and through it all, bit by bit, molecule by molecule, the dirt and oils and stains are lifted away, suspended, and washed down the drain. We'll travel through this process together tonight, slowly and thoroughly. From the moment water first enters the machine, through the gentle back and forth of the wash cycle, past the chemistry that happens between soap and fabric, all the way to that final spin that leaves your clothes merely damp rather than soaking wet. We'll explore the drum that holds everything, the motor that drives it all, the heating elements that warm the water just so. We'll understand the sensors that measure, and the pumps that drain, and the cycles that repeat, until everything is as it should be. Before washing machines, people washed clothes by hand. They would fill large tubs or basins with water, often heated over a fire. They would scrub fabrics against washboards, their hands working back and forth for hours. Then they would wring the clothes by hand or through mechanical wringers, trying to squeeze out as much water as possible before hanging everything to dry. It was exhausting work, time-consuming work, work that left hands raw and backs aching. The first washing machines were simple improvements on this basic process. They were tubs with hand-cranked agitators, wooden paddles that would move back and forth through the water when you turned a handle. Later came electric motors, small at first, barely powerful enough to move wet clothes through water. But engineers kept improving them. They added automatic timers so the machine would know when to stop. They added pumps so water could be drained away without buckets. They added heaters so water could be warmed without kettles from the stove. They added multiple rinse cycles and spin cycles and all manner of helpful features. Today's washing machines are marvels of engineering, even the simple ones. Inside that metal or plastic cabinet sits a system of precisely calibrated components. There are valves that open and close at just the right moments, motors that can spin at different speeds, pumps that can move gallons of water in minutes, sensors that can measure water level and temperature and load balance, control circuits that coordinate everything, turning each component on and off in exactly the right sequence. And it all happens so quietly now, so smoothly, that we barely think about it. We simply load our clothes, pour in detergent, select a cycle, and walk away. The machine does the rest. But tonight, we're not going to walk away. We're going to stay and watch in our mind's eye as every single step unfolds. We're going to understand exactly what happens and exactly why, from the very first drop of water to the very last spin of the drum. So let yourself relax a little more now. There's a whole journey ahead, and we're going to take it slowly, one gentle step at a time. By the time we're done, you'll understand the complete cycle, every phase, every process, every piece working together. And along the way, perhaps you'll drift off to sleep, lulled by the steady rhythm of explanation, the soft cadence of discovery. Let's begin at the very beginning. Let's start with something as simple as water. Before anything else can happen, before any cleaning can begin, the washing machine needs water. This seems obvious, simple even. But the way water enters a washing machine is actually quite sophisticated. It's not just a matter of opening a faucet. There are valves to control, temperatures to mix, pressures to manage, and filters to protect the whole system. So let's slow down and examine exactly how water finds its way into your machine. Behind your washing machine, usually near the floor, there are two hoses. One is connected to your home's cold water supply, and the other is connected to the hot water supply. These hoses are typically threaded onto connections at the back of the machine. They're flexible, often made of reinforced rubber or braided stainless steel, designed to withstand the water pressure from your home's plumbing without leaking or bursting. These hoses lead to a component called the water inlet valve. This valve is mounted on the back of the washing machine, and it's the gatekeeper for all water entering the machine. It's a mechanical and electrical component, beautifully simple in its design, yet perfectly suited to its task. Inside the inlet valve are small gates, one for hot water and one for cold water. These gates are normally closed. They're held shut by springs, sitting there quietly, waiting. But each gate is controlled by a solenoid, which is essentially an electromagnet wrapped in a coil. When electricity flows through the coil, it creates a magnetic field. This magnetic field pulls on a small metal plunger, and that plunger opens the gate, allowing water to flow through. The beauty of this design is its precision. The washing machine's control system can send electrical signals to either solenoid or both whenever water is needed. If the cycle calls for cold water, electricity flows to the cold water solenoid. The gate opens. Cold water rushes through. If the cycle calls for warm water, both solenoids receive power. Both gates open. Hot and cold water mix together as they enter the machine. And if the cycle calls for hot water only, well, you can probably guess. Just the hot water solenoid receives power. Just that gate opens, and only hot water flows in. The water pressure from your home's plumbing does most of the work. Typical household water pressure ranges from about 40 to 80 pounds per square inch. That's plenty of force to push water through the inlet valve, through the internal plumbing of the washing machine, and into the drum. The solenoid doesn't have to work very hard. It just has to open the gate. The pressure does the rest. But there's more happening here than you might think. Just inside each inlet port, Before the water reaches the solenoid gates, there's a small mesh screen. This screen is fine, with tiny openings that allow water to pass but catch debris. Because the water coming from your home's plumbing isn't perfectly pure, it might contain small particles of sediment, especially if you have older pipes. It might have tiny bits of mineral build-up. It might even have small pieces of pipe scale or other debris that has broken loose somewhere in the plumbing system. These filter screens catch all of that. They protect the solenoid valves from getting clogged or damaged. They protect the internal plumbing of the washing machine. They ensure that only clean water, free of particles, makes its way into the drum where your clothes are waiting. Over time, these screens can accumulate buildup, especially in areas with hard water. That's why sometimes, if a washing machine seems to be filling slowly, cleaning these filter screens can restore normal flow. Once water passes through the inlet valve, it travels through small diameter tubing inside the machine. This tubing routes the water to the detergent dispenser, which we'll explore in detail soon. For now, just know that the water doesn't go directly to the drum. It makes a stop first, flowing through the compartments where you've placed detergent and fabric softener, picking up those cleaning agents, carrying them along as it continues its journey toward the waiting clothes. The inlet valve opens and closes based on water level. Inside the washing machine, there's a pressure sensor or a water level switch. As water fills the drum, the air pressure inside a special chamber changes. This pressure change signals to the control system that water is rising. When the water reaches the correct level for the selected cycle, the control system stops sending power to the solenoid valves. The gates close. The springs pull them shut. Water stops flowing. Different cycles require different amounts of water. A small load on a delicate cycle might use just a few gallons. A large load on a heavy-duty cycle might use 15 gallons or more. Some modern high-efficiency machines use even less, detecting the size and weight of the load and adding only the minimum water needed to properly clean the clothes. But whatever the amount, the inlet valve is what controls it, opening and closing in response to signals from the control system. Always precise, always reliable. The temperature of the water matters too, and it's controlled by how long each solenoid stays open. If you want warm water, both hot and cold flow simultaneously, mixing together. The longer the hot water valve stays open relative to the cold, the warmer the final temperature. The washing machine doesn't have a thermometer measuring the water as it enters. Instead, it relies on your home's water heater to provide hot water at a relatively consistent temperature, usually around 120 degrees Fahrenheit. Cold water varies more depending on the season and your location, but it's typically somewhere between 50 and 70 degrees Fahrenheit. By mixing these two sources in different proportions, the machine can achieve a range of temperatures. A cold wash uses only the cold water supply. A warm wash might mix equal parts hot and cold, resulting in water around 80 to 90 degrees. A hot wash uses mostly hot water, perhaps with just a touch of cold to moderate the temperature slightly, ending up around 110 to 120 degrees. Why does temperature matter? Because temperature affects how well detergent works. It affects how quickly dirt and oils dissolve. It affects the chemical reactions that break down stains. Hot water is better at removing greasy stains and heavily soiled items because heat helps dissolve oils and makes chemical reactions happen faster. Cold water is gentler on fabrics and saves energy since you're not using your water heater. Warm water is a compromise, effective for most everyday loads without being too harsh on fabrics or too demanding on energy. Some washing machines have a heating element built in, allowing them to heat the water further once it's inside the drum. We'll explore that component later. But even machines with internal heaters start with water from the inlet valve. Water that comes from your home's plumbing at whatever temperature your water heater provides. The inlet valve system is simple, but it's also critical. Without it, there would be no water. Without water, there would be no washing. It's the first step, the foundation on which everything else builds. Water flows in, controlled precisely, at the right temperature, in the right amount, carrying with it the potential for clean clothes. And so the drum begins to fill. Water streams in, finding its way around the clothes you've loaded, soaking into the fabric, beginning the slow work of loosening dirt and preparing for the wash cycle ahead. But the water doesn't arrive alone. It brings something else with it, something essential to the cleaning process. It brings detergent. When you pour detergent into your washing machine, you're probably placing it in a small drawer or compartment, usually located on the top front of a front-loading machine or somewhere accessible on a top-loading machine. This drawer might seem simple, just a plastic box with a few sections. But the way it delivers detergent to your clothes at exactly the right moment is actually quite clever. Most detergent drawers have 3 compartments. They're often labeled, though the symbols can vary by manufacturer. Typically, one compartment is for pre-wash detergent, another is for main wash detergent, and the third, usually the smallest, is for fabric softener. Each compartment serves a specific purpose, and each releases its contents at a different time during the wash cycle. The pre-wash compartment is for cycles that include an initial wash before the main wash. This is useful for heavily soiled items. If you select a cycle with a pre-wash, water flows through this compartment first, washing away the detergent you placed there and carrying it down to the drum. The clothes get a preliminary cleaning, loosening the worst of the dirt. Then that water drains away, and the main wash cycle begins with fresh water and main wash detergent. The main wash compartment is where you place detergent for the regular wash cycle. This is the compartment you'll use most often. When the machine fills with water for the main wash, the water flows through this compartment, dissolving the detergent and carrying it to the drum. The compartment is designed so that water enters at the top or back and flows down through the detergent, ensuring complete dissolution and transfer. Some main wash compartments have a small flap or divider. If you're using liquid detergent, you might need to flip this flap down. The flap creates a small reservoir that holds the liquid detergent temporarily, preventing it from draining into the drum prematurely. When water flows through, it washes the liquid detergent away completely. If you're using powder detergent, the flap stays up, allowing the water to flow through more directly and carry the powder along. The fabric softener compartment works differently. Fabric softener isn't needed during the wash cycle. In fact, adding it too early would interfere with cleaning because fabric softener coats fibers, and you want those fibers exposed so detergent can clean them. Instead, fabric softener is added during the rinse cycle, after the detergent and dirt have been washed away. But how does the machine know to release the fabric softener at the right time? The answer is water flow. During the main wash and the early rinses, water flows through the pre-wash and main wash compartments, but not through the fabric softener compartment. The internal design of the dispenser drawer directs water along certain paths. But during the final rinse, water is routed differently. It flows through the fabric softener compartment, flushing out the softener and carrying it down to the drum, where it can coat the clean fabrics, making them feel softer and reducing static cling. Some washing machines have automatic dispensers, especially newer models. These machines have larger reservoirs for detergent and fabric softener, enough for multiple loads. You fill these reservoirs, and the machine automatically dispenses the right amount for each load based on the cycle you select and the load size. Sensors detect the weight of the clothes, and the control system calculates how much detergent is needed. Then a small pump or valve releases precisely that amount from the reservoir, mixing it with the incoming water. These automatic systems are convenient, but the principle is the same. Detergent must be dissolved in water and delivered to the clothes at the right time. Whether it's a simple drawer with compartments or a sophisticated automatic dispenser, the goal is to ensure that detergent reaches the fabric when it can do the most good. The path from the detergent drawer to the drum is short but important. After water picks up the detergent, it flows down through internal channels, usually entering the drum at the top. In front-loading machines, water often enters through small openings or jets at the back of the door seal or at the top of the drum. In top-loading machines, water might spray in from the sides or flow down from the top center. Either way, it enters the drum already mixed with detergent, ready to begin cleaning. The amount of detergent you add matters. Too little, and clothes won't get as clean as they could. Too much, and you end up with excess suds that can interfere with washing and are hard to rinse out completely. Detergent manufacturers provide guidelines on the bottle, usually suggesting an amount based on load size and water hardness. High-efficiency machines, in particular, require less detergent because they use less water. The detergent is more concentrated in the smaller volume of water, so a little goes a long way. Powder detergents dissolve in water, though this takes a moment. As water flows through the compartment, it begins dissolving the powder, carrying some of it away immediately and continuing to work on the rest. By the time all the water has flowed through, all the powder should have dissolved and been carried to the drum. Liquid detergents mix more readily, dispersing into the water almost instantly. Some people place detergent directly in the drum rather than in the dispenser drawer. This can work, especially with liquid detergent or detergent pods. Pods, those small packets of concentrated detergent wrapped in a dissolvable film, are designed to be placed directly on or with the clothes. When water enters the drum, it dissolves the film, releasing the concentrated detergent exactly where it's needed. But using the dispenser drawer has advantages. It ensures even distribution. It allows pre-wash and main wash detergent to be added at different times. It keeps fabric softener separate until the final rinse. And it means you're not pouring detergent directly onto dry clothes, where it might not dissolve evenly or might leave residue on certain items. The chemistry that happens when detergent mixes with water is fascinating, and we'll explore it in depth soon. But for now, just know that as the drum fills with water, that water is already working, already carrying the chemical agents that will do most of the cleaning. The stage is set. Water is in the drum, mixed with detergent. Clothes are soaking, fibers swelling as they absorb water. And now, the real work is about to begin. But before we move on to what happens next, let's take a moment to appreciate what we've covered so far. Water has entered through carefully controlled valves at precisely the right temperature. It has flowed through compartments designed to pick up detergent at exactly the right times. And now that water, enriched with cleaning agents, surrounds your clothes, seeping into every fiber, preparing for the agitation and tumbling that will come next. Everything so far has been gentle, quiet, preparatory. The loudest sound might be the rush of water entering the drum, a soft whoosh that gradually fades as the water level rises. There's no motion yet, no spinning or sloshing, just stillness, the calm before the rhythm of the wash cycle begins. And in that stillness, chemistry is already starting to happen. Detergent molecules are beginning their work. But to truly understand what they're doing, we need to explore the science of cleaning itself. Cleaning clothes is, at its heart, a chemical process. Water alone does a poor job of removing most kinds of dirt, especially oils and greases. That's where detergent comes in. Detergent is a carefully designed mixture of chemicals, each one chosen for specific cleaning properties. The most important ingredient in any detergent is something called a surfactant. This is the molecule that does most of the actual cleaning, and understanding how it works is key to understanding how your washing machine cleans your clothes. Let's take a moment to really understand dirt itself. What is it that makes clothes dirty? Well, dirt comes in many forms. There's visible dirt, the stuff you can see, mud particles, dust, food stains. But there's also invisible dirt. Oils from your skin transfer to clothes with every wear. Sweat contains salts and proteins that cling to fibers. Dead skin cells accumulate in fabric. Bacteria grow in the warm, moist environment that clothes provide during wear. All of these things need to be removed for clothes to be truly clean. Different types of dirt require different cleaning approaches. Particulate dirt, like mud or dust, consists of solid particles that get trapped in the weave of fabric. These particles can often be removed by mechanical action alone, though water helps by making the particles easier to dislodge. Greasy or oily dirt is much more challenging. Oils are hydrophobic, meaning they repel water. They cling tightly to fabric fibers, forming a coating that water cannot penetrate. This is where chemistry becomes essential. Protein-based stains, like blood, grass, or food, involve large, complex molecules that bind to fibers. These require enzymatic action to break them down into smaller pieces that can then be washed away. Mineral deposits from hard water can leave clothes looking dingy or feeling stiff. These require chelating agents to dissolve and remove them. And then there are dyes and pigments from foods or other sources that actually color the fabric itself. These can be among the most difficult stains to remove because the dye molecules have penetrated deep into the fiber structure. Water and oil don't mix. You've probably seen this if you've ever tried to wash greasy hands with water alone. The water beads up and runs off, leaving the grease behind. This happens because water molecules are attracted to each other much more strongly than they're attracted to oil molecules. Water forms a kind of skin on its surface, a property called surface tension. This surface tension prevents water from spreading out and contacting oily surfaces. So the water and the oil remain separate, and no cleaning happens. A surfactant is a molecule that changes this. The word surfactant is short for surface active agent, meaning it's active at the surface between water and other materials. Surfactant molecules have a very specific structure. One end of the molecule is hydrophilic, which means water-loving. This end is attracted to water molecules. The other end is hydrophobic, which means water-fearing. This end is repelled by water but attracted to oils and grease. When you add detergent to water, these surfactant molecules spread out through the water. The hydrophilic ends want to stay in the water, but the hydrophobic ends want to get away from it. So the surfactant molecules arrange themselves at interfaces, at the boundaries between water and other materials. They line up along surfaces, with their hydrophilic heads pointing into the water, and their hydrophobic tails pointing away from it. This arrangement reduces surface tension. The water no longer forms such a strong skin. It can spread out more easily. It can penetrate fabrics better. And crucially, those hydrophobic tails of the surfactant molecules are attracted to oils and greases. They burrow into greasy stains, wedging themselves between the oil and the fabric fibers. As more and more surfactant molecules attach to a spot of grease, they begin to surround it. Eventually they form a sphere around the grease, with all the hydrophobic tails pointing inward toward the grease, and all the hydrophilic heads pointing outward toward the water. This sphere is called a micelle. The grease is now trapped inside the micelle, completely surrounded by surfactant molecules. And because the outside of the micelle is covered with hydrophilic heads, the water can interact with it. The water can carry the micelle away, lifting the grease off the fabric and keeping it suspended in the water until it's rinsed down the drain. This is the fundamental mechanism of how soap and detergent clean. They make it possible for water to interact with oils and grease. They break the oil into tiny droplets and surround those droplets with a coating that makes them compatible with water. Then the water can wash them away. But surfactants aren't the only ingredient in laundry detergent. There are many others, each serving a specific purpose. Enzymes are common in what are called biological or enzyme detergents. Enzymes are proteins that speed up chemical reactions. In detergents, they're chosen for their ability to break down specific types of stains. Proteases break down protein-based stains like blood, grass, and food. Lipases break down lipid-based stains, which are fats and oils. Amylases break down starches. Each enzyme works like a tiny molecular scissor, cutting apart the large molecules that make up the stain and turning them into smaller molecules that are easier to wash away. Builders are another important ingredient. These are chemicals that soften water by binding to minerals like calcium and magnesium. Hard water contains these minerals, and they interfere with how well surfactants work. The minerals can bind to surfactant molecules, preventing them from forming micelles and lifting dirt. Builders prevent this by grabbing onto the minerals first, leaving the surfactants free to do their job. Common builders include phosphates, though these have been largely phased out due to environmental concerns, and alternative builders like citrates and zeolites. Brighteners are chemicals that make clothes appear whiter and colors appear brighter. They work by absorbing ultraviolet light and re-emitting it as visible blue light. This counteracts the yellowing that naturally occurs in fabrics over time. Your clothes aren't actually whiter, but they look whiter because they're reflecting more light in the blue range of the spectrum. Fragrances give laundry a pleasant smell. They're complex mixtures of aromatic compounds chosen to evoke freshness and cleanliness. Some detergents include fragrances designed to last, clinging to fabric fibers so your clothes smell fresh, even after they've been stored for a while. Anti-redeposition agents prevent dirt that has been lifted from the fabric from settling back onto the fabric. Once dirt is suspended in the water, you want it to stay suspended until the water drains away. These agents coat dirt particles, keeping them dispersed in the water. pH adjusters help maintain the right acidity or alkalinity. Most laundry detergents are slightly alkaline, which helps with cleaning because many stains are acidic. The alkaline detergent neutralizes the acid in the stain, making it easier to remove. Stabilizers and preservatives keep the detergent itself from degrading while it sits in the bottle or box. They prevent enzymes from breaking down and keep liquid detergents from separating. All of these ingredients work together. When detergent dissolves in the water filling your washing machine, each component begins its specific job. Surfactants lower surface tension and prepare to form micelles. Enzymes start looking for stains they can break down. Builders grab onto minerals in the water. Brighteners and fragrances wait to attach to fabric fibers during rinsing. Temperature plays a role too. Warmer water makes chemical reactions happen faster. Enzymes work better at warm temperatures. Surfactants are more effective at dissolving oils and greases when the water is hot. That's why heavily soiled items and greasy stains are often washed in hot or warm water. The heat accelerates the chemistry. But chemistry alone isn't enough. Even with perfect detergent in perfect water, dirt wouldn't come off very well if the clothes just sat there motionless. That's where the mechanical action comes in. The physical movement of clothes through water, rubbing against themselves and the drum, helps dislodge dirt and work the detergent deeper into fibers. This mechanical action is provided by the washing machine itself, through the design of the drum and the way the machine moves clothes during the wash cycle. And that's what we'll explore next. At the center of every washing machine is the drum. This is the large cylindrical chamber where you place your clothes. It's where all the action happens, where water mixes with fabric, where agitation occurs, where spinning happens. Understanding the drum's design and structure helps us understand how washing machines accomplish their task. If you look inside a washing machine drum, you'll see that it's not a solid cylinder. It's perforated, covered with hundreds or thousands of small holes. These holes serve several purposes. During washing, they allow water to flow freely between the inside of the drum, where your clothes are, and the outer tub that surrounds the drum. During spinning, they allow water to escape from the clothes, being flung outward through the holes by centrifugal force. Actually, there are two drums in a washing machine, though you only see one of them. The inner drum is the one you interact with, the one with the holes. This drum rotates during the wash and spin cycles. The outer drum, sometimes called the tub, is stationary. It holds the water and catches the water that flies out through the holes of the inner drum during spinning. The outer drum is watertight, sealed at the bottom to prevent leaks, and it's usually made of plastic or enameled steel. The inner drum is often made of stainless steel, which is durable, doesn't rust, and can withstand the constant exposure to water and detergent. Some machines use plastic drums, which are lighter and quieter, but less durable over the long term. Some use porcelain-coated steel, which combines the strength of steel with a smooth, stain-resistant coating. The size of the drum determines the capacity of the washing machine. A larger drum can hold more clothes, but it also requires a larger machine overall. Drum capacity is usually measured in cubic feet or kilograms, indicating how much laundry weight the machine can handle in a single load. Inside the drum, you'll often see raised ridges or paddles. These are called baffles or lifters. They serve an important purpose. As the drum rotates, these baffles catch the clothes and lift them up. Then, as the drum continues to turn, the clothes fall back down. This lifting and dropping action is crucial for washing, especially in front-loading machines. It ensures that clothes tumble through the water, exposing all surfaces to the cleaning action of the detergent. In a front-loading machine, the drum rotates on a horizontal axis. The door is on the front, and you load clothes horizontally into the machine. When the drum turns during washing, the clothes are lifted by the baffles and then tumble back down through the water. This tumbling action is gentle but effective. Gravity does most of the work, pulling the clothes back down, and the repeated lifting and dropping ensures every part of every garment gets exposed to water and detergent. In a top-loading machine, the drum axis is vertical. You load clothes from the top, looking down into the machine. The drum might rotate during washing, but often the cleaning action comes from a different mechanism, which we'll discuss in detail soon. Even in top loaders, though, the perforated drum design serves the same purpose, allowing water to flow through and around the clothes. The inner drum is mounted on a shaft, sometimes called a drum shaft or spin basket shaft. This shaft is what rotates, driven by the motor through a series of belts, pulleys, or direct drive mechanisms. The shaft is carefully balanced to minimize vibration, and it's supported by bearings, which allow it to spin smoothly with minimal friction. Between the inner drum and the outer tub, there's usually a suspension system. This system absorbs vibrations and prevents the spinning drum from shaking the entire machine apart. Springs or shock absorbers connect the outer tub to the machine's frame, allowing the tub to move slightly, but damping out the rapid oscillations that would otherwise occur during high-speed spinning. Water enters the space between the inner drum and outer tub. It flows through the holes in the inner drum, soaking the clothes. As the drum moves, the water sloshes and moves with it, constantly being redistributed around the load. This movement is important. It ensures that all clothes get wet, that detergent is distributed evenly, and that dirty water is continually being flushed through the fabric. The drum is designed to last for many years. It endures repeated cycles of filling, washing, rinsing, and spinning. It holds the weight of wet clothes, which can be substantial. A full load of wet laundry can weigh 50 pounds or more, and all of that weight is supported by the drum and its shaft and bearings. The drum must be strong enough to handle this without warping or cracking. At the same time, the drum must be smooth. There can't be sharp edges or rough spots that would snag fabric. The holes are usually punched or drilled with smooth edges, or they're molded into the plastic if it's a plastic drum. This smoothness protects your clothes from damage during washing. Some modern washing machines have drums with special designs. Honeycomb patterns with indented surfaces create a thin film of water between the clothes and the drum, reducing wear on fabrics. Larger lifters or paddles create more pronounced tumbling. Drums might be tilted at a slight angle to improve water circulation. Each design feature is carefully considered to balance cleaning effectiveness with fabric care. The drum is where your clothes spend their time during washing. It's their world for the next hour or so. And within that world, subjected to water and detergent and motion, a transformation takes place. Dirt is loosened, lifted, and washed away. Stains are broken down and dissolved. Fibers are rubbed gently against each other, helping to dislodge particles and work detergent deeper into the weave of the fabric. But the drum doesn't work alone. In top-loading machines especially, there's often another component that works with the drum to create the washing action. It's a component that many people are familiar with, one that's been a feature of washing machines for decades. It's called an agitator, and it's time we understood exactly what it does. When you think of a traditional top-loading washing machine, you probably picture a tall post in the center of the drum, a vertical column with fins or vanes spiraling up its length. This is the agitator, and its job is to create movement in the water and clothes during the wash cycle. It's one of the most recognizable parts of a washing machine, and it's been around in various forms for nearly as long as electric washing machines have existed. An agitator works through back and forth rotational motion. The post is connected to a shaft that runs down through the center of the drum. This shaft is driven by the washing machine's motor through the transmission. During the wash cycle, the agitator rotates back and forth, typically moving about a quarter turn in one direction, then a quarter turn in the other direction, then repeating this motion over and over. As the agitator moves, its fins push through the water and clothes. This creates currents in the water, swirling flows that move clothes around the drum. The motion is vigorous, rubbing clothes against the sides of the agitator, against the drum walls, and against each other. All of this rubbing helps dislodge dirt and work detergent into the fabric fibers. The agitator's back and forth motion is carefully timed. It usually oscillates several times per minute, creating a rhythm. The clothes move with this rhythm, shifting position constantly, ensuring that no part of any garment stays in the same place for long. This constant repositioning is important because it means every part of every garment gets exposed to the cleaning action. Agitators come in different designs. Single-action agitators move back and forth as a single piece. The entire post rotates together. Dual-action agitators have two parts. The base might rotate in one direction, while the top rotates in the opposite direction, or the entire agitator might move back and forth, while an inner part moves independently. This dual action creates even more turbulence in the water, theoretically improving cleaning performance. The fins on an agitator are angled. They're not just flat panels. They slope or twist, shaped to push water and clothes in specific directions as the agitator moves. Some agitators have fins that spiral up the post, creating a helical pattern that lifts clothes upward and then allows them to fall back down. Others have fins arranged in tiers, with each tier pushing clothes in slightly different directions. Agitators are effective, especially for heavily soiled loads. The vigorous motion and the rubbing action they create can tackle tough stains and ground-in dirt. But they have some downsides. They take up space in the center of the drum, reducing the amount of room available for clothes. A drum with an agitator can't hold as much laundry as a drum without one. Agitators can also be rough on delicate fabrics. The vigorous motion and the rubbing against the fins can cause wear or even damage to certain garments. This is why many modern top-loading washing machines have moved away from traditional agitators and toward a different design called an impeller. An impeller sits at the bottom of the drum instead of rising up from the center. It's a low-profile disc or cone with veins or ridges on its surface. During washing, the impeller rotates, and its veins push water and clothes around the drum. The motion created by an impeller is different from that created by an agitator. Instead of a back-and-forth oscillation, the impeller usually rotates in one direction, though it might reverse periodically. The rotation creates a current in the water, a circular flow that moves clothes around the drum. Clothes rub against each other and against the drum walls, but there's no central post for them to rub against. Impellers are gentler on clothes than agitators. They create less mechanical wear. They also free up more space in the drum, allowing for larger load capacities. But some people find that impellers don't clean as effectively as agitators, especially for heavily soiled items. The motion is less vigorous, and there's less direct rubbing action. Front-loading washing machines use a completely different approach. They have no agitator or impeller at all. Instead, they rely on tumbling. The drum rotates on a horizontal axis, and as it turns, the clothes are lifted by the baffles and then drop back down through the water. This lifting and dropping is repeated continuously throughout the wash cycle. Tumbling is gentle. Clothes aren't being pushed or pulled vigorously through water. They're simply being lifted and dropped over and over. Gravity provides the force, pulling clothes back down into the water after they've been lifted. This gentleness makes front-loading machines ideal for delicate fabrics. It also makes them more water-efficient. Front-loaders use less water than top-loaders, partly because they don't need to fill the drum completely. The tumbling action works even with a partial fill, as long as there's enough water to wet the clothes as they tumble through it. The speed of rotation varies during washing. In a front loader, the drum might rotate slowly during most of the wash cycle, giving clothes time to be lifted, reach the top of the rotation, and then tumble down through the water. The rotation is fast enough to lift clothes, but slow enough that they don't just spin around stuck to the drum wall. This is a delicate balance, achieved through careful control of the motor speed. In agitator and impeller machines, the speed of oscillation or rotation is also carefully controlled. Too fast, and the motion becomes chaotic, tangling clothes rather than cleaning them. Too slow, and there isn't enough agitation to loosen dirt. Manufacturers test different speeds and patterns to find the optimal motion for cleaning. Some modern machines have multiple motion patterns. They might agitate in one direction for a few seconds, then reverse for a few seconds. They might pause briefly between strokes. They might vary the speed or intensity of agitation during different parts of the wash cycle. These variations help improve cleaning by exposing clothes to different types of motion, preventing them from settling into stable positions where some parts don't get cleaned as well. The agitation or tumbling phase of the wash cycle typically lasts for several minutes. During this time, the combination of water, detergent, and motion works on the clothes. Surfactants attach to oils and grease. Enzymes break down stains. Physical rubbing dislodges particles. Water flows through fabric, carrying away dissolved dirt. And gradually, incrementally, the clothes become cleaner. But agitation doesn't happen continuously throughout the entire wash cycle. There are pauses. Sometimes the machine stops for a moment, allowing water and clothes to settle. This settling can help with certain types of cleaning. It gives surfactant molecules time to work without being constantly disturbed by motion. It allows dirt that's been lifted from fabric to disperse into the water rather than potentially being redeposited on another garment. After a period of agitation, the machine drains the dirty water. This water, now full of detergent, suspended dirt, oils, and everything else that was on your clothes, flows out through the drain pump and into your home's wastewater system. And then, with the wash phase complete, the machine moves on to the next stage: rinsing. But before we discuss rinsing, we should understand one more component that plays a crucial role in how washing machines work. We should understand the motor, the source of all this motion, the component that drives everything else. Every washing machine needs a motor. This electric motor is the heart of the machine, the component that provides the power for all the motion. It drives the drum. It drives the agitator or impeller. It drives the pump that drains water. Understanding how this motor works and how its power is transmitted to the various components helps us appreciate the engineering that makes washing machines possible. Most washing machines use a type of electric motor called an induction motor. Induction motors are reliable, simple in design, and well suited to the demands of washing machine operation. They work on the principle of electromagnetic induction. Inside the motor, there's a rotating part called the rotor and a stationary part called the stator. The stator contains coils of wire. When alternating current flows through these coils, it creates a rotating magnetic field. This rotating field induces currents in the rotor, and these currents create their own magnetic field. The interaction between the two magnetic fields causes the rotor to spin, following the rotating field created by the stator. Induction motors don't need physical contact between the stationary and rotating parts. There are no brushes or commutators like you'd find in other types of electric motors. This makes them very durable. There's less that can wear out. They can run for years, through thousands of wash cycles, with minimal maintenance. The motor in a washing machine doesn't run at a constant speed. It needs to be able to spin at different speeds for different parts of the cycle. During washing, the motor might spin relatively slowly, turning the agitator back and forth or rotating the drum gently for tumbling. During the spin cycle, the motor spins very fast, rotating the drum at high speed to extract water from the clothes. The motor needs to be able to transition smoothly between these speeds and to reverse direction when needed. Speed control is often achieved through the motor's design and the way it's powered. Some motors have multiple windings that can be engaged separately, allowing for different speed settings. Others use electronic controls that vary the frequency or voltage of the electricity supplied to the motor, controlling the speed that way. The motor's power must be transmitted to the drum and other components. This transmission can happen in several ways. In many traditional washing machines, the motor drives a belt. This belt wraps around a pulley on the motor shaft and another pulley connected to the transmission or directly to the drum shaft. As the motor spins, the belt transfers the rotational motion to the drum. Belts have advantages. They're simple. They're relatively inexpensive to replace if they wear out. They provide some cushioning, absorbing sudden changes in load and protecting the motor from shock. But belts can wear out over time. They can slip if they become loose. They can break if they become brittle or damaged. Some washing machines use a direct drive system instead. In a direct drive machine, the motor is mounted directly beneath the drum, and its shaft is connected directly to the drum or agitator shaft. There's no belt, no pulleys. The motor's rotation directly becomes the drum's rotation. Direct drive systems are simpler in some ways. There's no belt to maintain or replace. They can be more efficient because there's no energy lost to belt friction or slippage. They can also be quieter because there's no belt moving over pulleys. But direct drive systems put more stress on the motor. The motor must handle all the load directly, including the weight of wet clothes and the resistance during agitation. The motor must be more robust, and the bearings supporting the drum shaft must be especially durable. Regardless of how power is transmitted, the motor works in coordination with other components. In top-loading machines with agitators, there's often a transmission. The transmission is a mechanical device, somewhat like a car's transmission, that changes the motor's rotational motion into the back and forth oscillation needed for the agitator. It also allows the drum to spin at high speed during the spin cycle, while the agitator remains stationary. The transmission contains gears and clutches. During washing, one clutch engages, connecting the motor to the agitator shaft. The gears convert the motor's rotation into oscillation, moving the agitator back and forth. During spinning, a different clutch engages, connecting the motor to the drum and allowing the entire basket to spin freely. The agitator doesn't move during spinning, or it might even lock in place to prevent it from oscillating. Modern washing machines increasingly use advanced motor technologies. Some use brushless DC motors, which are even more efficient and longer-lasting than traditional induction motors. Some use what's called an inverter motor, where electronic controls vary the speed very precisely, allowing for complex motion patterns and optimal energy use. All of these motors and drive systems serve the same purpose: to create controlled motion. That motion is what makes washing possible. Without motion, clothes would just soak in water and detergent, and while that would do some cleaning, it wouldn't be very effective. The motion is what creates the rubbing, the tumbling, the agitation that dislodges dirt and works detergent deep into fibers. And yet, motion alone isn't enough. Temperature matters too. For certain types of stains and certain levels of soiling, warm or hot water cleans much better than cold water. That's where another component comes in, one that's present in many washing machines and plays a crucial role in achieving optimal cleaning performance. It's the heating element. Water enters most washing machines at whatever temperature your home's plumbing provides. Cold water comes from your cold water line, typically somewhere between 50 and 70 degrees Fahrenheit, depending on the season and your location. Hot water comes from your water heater, usually around 120 degrees Fahrenheit. By mixing these two sources, the machine can achieve a range of temperatures. But some washing machines go a step further. They have an internal heating element, allowing them to heat the water further once it's inside the machine. This heating element is a crucial component in many front-loading machines and some high-end top-loaders, especially those designed to meet efficiency and performance standards. The heating element is typically located at the bottom or side of the outer tub, immersed in the water or positioned where water will flow around it. It's usually a metal tube, often made of stainless steel or copper, bent into a shape that maximizes surface area. Inside this tube is a resistance wire. When electricity flows through this wire, the electrical resistance causes the wire to heat up. The heat transfers through the tube wall and into the water surrounding it. This is a simple but effective design. Resistance heating is straightforward. The amount of heat produced depends on how much current flows and how long the element is energized. The washing machine's control system monitors the water temperature with a sensor, usually a thermistor, which is a component whose electrical resistance changes with temperature. Based on readings from this sensor, the control system turns the heating element on or off to maintain the desired temperature. Heating water inside the machine has several advantages. It allows precise temperature control. Even if your water heater is set to a certain temperature, there can be variation. Water cools as it travels through pipes. On cold days, the hot water might not be as hot by the time it reaches the machine. An internal heating element can compensate, ensuring the wash water reaches and maintains the exact temperature the cycle calls for. Certain wash cycles, especially in European-style front-loading machines, are designed to heat water to quite high temperatures, sometimes 140 or even 160 degrees Fahrenheit. These high temperatures are very effective at killing bacteria and removing greasy stains. They're particularly useful for washing items like towels, bedding, and heavily soiled work clothes. The heating element doesn't run continuously. It cycles on and off as needed. At the start of the wash cycle, if the incoming water is cooler than the target temperature, the element turns on. Water temperature gradually rises. Once the target temperature is reached, the element turns off. If the temperature drops as heat is lost to the environment, or as cooler rinse water is added later, the element might turn back on briefly to bring the temperature back up. Heating water requires energy. An electric heating element uses a significant amount of electricity, typically between 1,500 and 2,500 watts. Over the course of a wash cycle, this can add up. That's why many modern machines are designed to minimize the need for heating. They use efficient wash algorithms that achieve good cleaning with lower temperatures. They use less water, so each gallon of water that is heated contributes more to the wash. They have better insulation around the tub to reduce heat loss. Some machines offer an eco or energy-saving mode that avoids heating water or uses only minimal heating. These modes take longer because cold water cleaning is less efficient chemically, so the machine compensates with longer wash times to achieve similar results. But the energy savings can be substantial, making these modes attractive for everyday loads that aren't heavily soiled. The heating element is controlled by a thermostat, or more commonly in modern machines, by the main control board based on sensor inputs. The control board monitors water temperature continuously. It knows what temperature the cycle calls for. It compares the actual temperature to the target temperature and decides whether to turn the heating element on or off. This closed-loop control system ensures that water temperature stays within the desired range. For safety, there's usually a high-limit thermostat as well. This is a backup safety device that turns off the heating element if the temperature gets too high. It prevents overheating, which could damage the machine or create a burn hazard. If the main control system fails and the heating element stays on too long, the high-limit thermostat cuts power to the element, preventing a dangerous condition. Over time, heating elements can accumulate mineral deposits, especially in areas with hard water. Calcium and magnesium in the water can precipitate out and form a chalky layer on the element surface. This layer insulates the element, reducing its efficiency. It takes longer to heat the water, and the element might overheat because the heat can't transfer to the water as efficiently. Regular maintenance, such as running a cleaning cycle with a descaling agent, can help prevent this build-up and keep the heating element working efficiently. Temperature affects more than just cleaning power. It also affects how long it takes for the wash cycle to complete. Heating water takes time, and if the machine must wait for water to reach a certain temperature before starting agitation, the cycle is extended. That's why hot wash cycles are often longer than cold wash cycles. The extra time is mostly spent heating. Temperature also affects the fabric. Hot water can cause some fabrics to shrink. It can set certain types of stains, like protein-based stains, making them harder to remove. That's why it's important to follow care labels on clothing. A garment that should be washed in cold water might be damaged if washed in hot water, even if the hot water would clean it more effectively. The heating element, then, is a tool. It gives the washing machine the ability to heat water to the optimal temperature for each load. It allows for flexibility in cleaning, making the machine more effective for a wider range of fabrics and stain types. And it works quietly, invisibly, doing its job behind the scenes while you load clothes and select cycles. With water at the right temperature, mixed with detergent, and with the drum or agitator creating motion, the wash cycle is in full swing. Clothes are being cleaned, dirt is being lifted away, stains are being broken down. And after several minutes of this vigorous activity, it's time for the next phase. It's time to rinse. The wash cycle is the heart of the cleaning process. This is when water, detergent, motion, and time all come together to remove dirt from your clothes. Understanding the wash cycle means understanding how these elements are coordinated, how they work together in a carefully timed sequence to achieve the best cleaning results. A typical wash cycle begins with filling. The washing machine's control system opens the water inlet valves, allowing water to flow into the drum. As we've discussed, water flows through the detergent dispenser first, picking up detergent and carrying it to the drum. The drum gradually fills, the water level rising around the clothes you've loaded. How much water is added depends on several factors. The cycle you've selected plays a role. A delicate cycle might use more water to create a gentler washing environment. A normal cycle uses a moderate amount. An eco cycle might use less water to save resources. The size of the load also matters. Many modern machines have sensors that detect the weight or volume of the load and adjust water level accordingly. A small load needs less water. A large load needs more. In traditional top-loading machines, water fills until it covers the clothes, creating a pool in which they can move freely. In front-loading machines and high-efficiency top-loaders, less water is used. The clothes might not be completely submerged. Instead, water is added until the clothes are thoroughly wet, and then tumbling or agitation redistributes that water, continuously wetting and re-wetting the fabric as it moves through the limited water volume. Once the drum has filled to the correct level, the washing machine pauses briefly. This pause allows the water and detergent to soak into the fabric. Fibers absorb water, swelling slightly. This swelling helps loosen dirt that's embedded in the fabric. Detergent begins its chemical work, with surfactant molecules attaching to oils and greases, beginning the process of forming micelles. Then agitation or tumbling begins. In a top-loading agitator machine, the agitator starts its back and forth motion. The clothes move with it, swirling through the water, rubbing against each other in the drum. In an impeller machine, the impeller rotates, creating currents that move clothes around the drum. In a front-loading machine, the drum rotates slowly, lifting clothes and allowing them to tumble back down through the water. This motion continues for several minutes, typically anywhere from 5 to 15 minutes depending on the cycle and the machine. The exact pattern of motion varies. Some machines agitate continuously. Others use a pattern of agitation followed by short pauses, then more agitation. These pauses allow the wash water to drain through the fabric, carrying dissolved dirt with it, and give time for surfactants to work without being constantly disturbed. The motion isn't just random, it's carefully designed. Engineers have spent years testing different patterns to find what cleans best while being gentle on fabrics. The speed of agitation, the duration of each stroke, the length of pauses between strokes, all of these have been optimized. Front-loading machines might vary the speed of the drum rotation, sometimes turning slowly for gentle washing, sometimes speeding up slightly for more vigorous action. During washing, you might hear the machine's sounds change, the swishing of water, the hum of the motor, the gentle thump as clothes tumble and hit the drum. These sounds are the audible evidence of the mechanical work being done, the physical processes that complement the chemical cleaning. As the wash cycle progresses, the water in the drum gradually becomes dirtier. It picks up the oils and dirt and stains that the detergent has lifted from the fabric. The water changes color, sometimes visibly so if the load was heavily soiled. This dirty water is full of suspended particles, oils trapped in micelles, dissolved salts and minerals, and diluted detergent. After the main agitation period, the machine drains the wash water. The drain pump activates, pulling water out of the outer tub and sending it through the drain hose to your home's wastewater system. As water level drops, clothes might continue to move slightly, helping to expel more water from the fabric. In top loaders, the agitator might make a few final slow rotations as the water drains. With the dirty wash water gone, the drum contains damp clothes still saturated with some detergent and dissolved dirt. This residue needs to be removed, which is why we need rinsing. But before rinsing begins, some machines perform a brief spin. This initial spin is often called a spin or drain spin. The drum rotates at a moderate speed, using centrifugal force to throw water out through the perforations. This removes much of the dirty water still clinging to the fabric, making the rinse cycle that follows more effective. This spin isn't as fast as the final spin cycle. It's just fast enough to expel most of the free water without putting too much stress on the fabrics. After a minute or so of spinning, the drum slows to a stop, and the machine is ready for the next phase. The wash cycle, then, is a carefully choreographed sequence. Fill with water and detergent. Pause to let everything soak. Agitate or tumble to loosen dirt. Pause to let chemistry work. Agitate more. Drain the dirty water. Spin briefly to expel excess water. Each step builds on the one before. Each contributes to the overall goal of cleaning. And now, with the wash complete and the dirty water drained away, it's time to rinse away the remaining detergent and any lingering dirt. It's time for fresh water, for a new cycle of filling and agitating and draining, but this time without detergent, focused solely on removing what remains. Rinsing is essential. Even though most of the dirt has been removed during the wash cycle, there's still detergent residue in the fabric. There might be suspended particles of dirt still clinging to fibers. There are minerals and salts from the wash water. All of this needs to be flushed away. That's what the rinse cycle does. It replaces the detergent-laden water with fresh water, diluting and removing any remaining contaminants. A rinse cycle begins much like a wash cycle. The water inlet valves open and fresh water flows into the drum. But this time, the water doesn't pass through the detergent dispenser, or if it does, it flows through a path that doesn't pick up any detergent. The goal is to add pure water, or as pure as the water from your tap can be. The amount of water added during rinsing is often similar to the amount used during washing. You want enough water to thoroughly flush the fabric. Too little water, and the rinse won't be effective. Detergent will remain, and your clothes might feel stiff or slippery, and they might irritate sensitive skin. Once the drum has filled with rinse water, the machine agitates or tumbles again. The motion is usually similar to the wash cycle, though it might be slightly gentler. The purpose is to move water through the fabric, flushing out any detergent and dirt that's still there. As the clothes move, rinse water flows through them, diluting the residue and carrying it away. This rinse agitation typically lasts for a few minutes. It doesn't need to be as long as the wash agitation because there's less work to do. The dirt has already been loosened. The rinse is just removing what's left. After rinsing, the water drains away just as the wash water did. The drain pump activates, water flows out, and the drum is left with damp clothes. But one rinse usually isn't enough to remove all the detergent, especially if you used a lot of detergent or if you have a large load. That's why most wash cycles include at least 2 rinses, and some include 3 or even more. Each rinse cycle follows the same pattern. Fill with fresh water. Agitate or tumble to flush the fabric. Drain the water. The first rinse removes most of the detergent residue. The second rinse removes most of what the first rinse left behind. If there's a third rinse, it removes almost all traces. With each successive rinse, the water that drains away is cleaner, less soapy, less cloudy, until finally the rinse water runs nearly clear. Between rinses, the machine might perform brief spins to expel water from the clothes. These intermediate spins aren't as intense as the final spin cycle, but they help. They reduce the amount of rinse water needed because they remove so much of the previous rinse water before the next rinse begins. Fabric softener, if you're using it, is added during one of the rinse cycles, typically the final rinse. As we discussed earlier, water flows through the fabric softener compartment of the dispenser drawer, picking up the softener and carrying it to the drum. Fabric softener contains chemicals that coat fabric fibers, making them feel softer and reducing static electricity. These chemicals need to be added after all the detergent has been rinsed away because they would interfere with cleaning if added earlier. Fabric softener works by depositing a thin layer of lubrication on the fibers. This makes towels feel fluffier, makes clothes feel smoother against your skin, and reduces the friction between fibers that causes static cling. It also adds a fragrance, leaving your clothes smelling fresh. Some people choose not to use fabric softener. It's not necessary for cleaning, and some fabrics, like athletic wear with moisture-wicking properties, can be negatively affected by softener. The coating can reduce the fabric's ability to wick moisture away from the skin. So whether to use fabric softener is a personal choice, based on your preferences and the types of clothes you're washing. Rinse water temperature is usually cold. There's no need to heat rinse water in most cases. Cold water rinses just as effectively as warm water, and using cold water saves energy. It also helps set the temperature of the clothes, cooling them down if they were washed in hot water. This cooling can be beneficial for certain fabrics, reducing wrinkling and helping clothes keep their shape. Some cycles offer a warm rinse option. This can be helpful for certain types of loads or in cold climates where the cold water supply is extremely cold. A warm rinse might help prevent temperature shock to fabrics, and it can make clothes feel more comfortable to handle when you take them out of the machine. But most of the time, cold rinses are perfectly adequate. The rinse cycle might seem simple compared to the wash cycle, but it's just as important. Without thorough rinsing, your clothes would come out of the machine feeling unpleasant. They might smell strongly of detergent. They might feel stiff or slick. They might irritate your skin or cause allergic reactions. And residual detergent can attract dirt more quickly, meaning your clothes would get dirty again faster. After the final rinse and drain, the machine is almost done. The clothes have been washed and rinsed. They're clean now, truly clean, free of dirt and detergent. But they're still very wet. They're saturated with water, heavy and dripping. Before you can take them out and dry them, that water needs to be removed. And that's what the final stage of the cycle does. It's time for the spin. The spin cycle is where the washing machine transforms from a gentle cleaning vessel to a powerful centrifuge. The drum, which has been rotating slowly or oscillating gently during washing and rinsing, now accelerates to much higher speeds, spinning faster and faster until the clothes inside are pressed against the drum walls by centrifugal force. And in that high-speed rotation, water is extracted from the fabric, flung outward through the drum's perforations, leaving clothes damp, but no longer dripping. Spin speeds are measured in revolutions per minute, or RPM. During washing, the drum might rotate at 50 or 100 revolutions per minute, or it might oscillate back and forth without completing full rotations. But during the spin cycle, speeds can reach 800, 1000, 1200, even 1600 revolutions per minute or higher in some machines. At these speeds, the drum is completing multiple rotations every single second. The physics behind water extraction during spinning is straightforward. When the drum rotates, everything inside experiences centrifugal force. This is the apparent force that pushes objects outward from the center of rotation. The faster the rotation, the stronger this force. At high spin speeds, the centrifugal force can be many times stronger than the force of gravity. Clothes are pushed outward against the drum wall. Water in the clothes is also pushed outward, but water can escape through the perforations in the drum. The clothes can't, so the water is forced out through the holes, flying through into the space between the inner drum and outer tub. From there, it drains down to the bottom of the outer tub and is pumped away by the drain pump. The amount of water removed depends on the spin speed and the duration of the spin. Higher speeds extract more water. A 1,600 revolutions per minute spin removes significantly more water than an 800 revolutions per minute spin. The difference can be noticeable. Clothes spun at higher speeds come out much drier, sometimes almost dry to the touch for thin fabrics. Clothes spun at lower speeds are wetter, taking longer to air dry or requiring more time in a dryer. But higher spin speeds also put more stress on fabrics. The centrifugal force pulling on fibers can cause stretching or damage, especially for delicate items. That's why different types of laundry call for different spin speeds. Heavy items like towels, jeans, and bedding can handle high-speed spinning. In fact, they benefit from it because the faster spin removes more water, reducing drying time. Delicate items like lingerie, sweaters, and silk garments need slower spin speeds to prevent damage. Many washing machines offer adjustable spin speeds, allowing you to choose the appropriate speed for each load. The spin cycle doesn't start at full speed immediately. If it did, the sudden acceleration would throw clothes around violently, potentially damaging them or unbalancing the load. Instead, the spin starts gently. The drum begins to rotate slowly, gradually picking up speed. This gradual acceleration allows clothes to distribute themselves somewhat evenly around the drum. As speed increases, centrifugal force presses them against the drum wall, and they spread out naturally. Modern washing machines have sensors that detect load balance. If the load is unevenly distributed, with most of the weight on one side of the drum, the machine will spin unevenly. This can cause violent vibrations and loud banging noises. It can even cause the machine to walk across the floor. To prevent this, if the sensors detect an imbalance, the machine stops spinning and attempts to redistribute the load. It might reverse direction briefly, or it might rock the drum back and forth, encouraging clothes to shift position. Then it tries spinning again. If the load is better balanced, the spin continues. If not, the machine might try redistributing a few more times before giving up and spinning at a reduced speed. During the spin cycle, you might hear the pitch of the motor change as the drum accelerates. There's a rushing sound, air moving through the drum as it spins. There might be a rhythmic thumping if the load isn't perfectly balanced. And you'll hear water draining, flowing from the outer tub down to the drain pump. The spin cycle typically lasts for several minutes. The exact duration depends on the machine and the cycle you've selected. Some cycles have longer spins to extract as much water as possible. Others have shorter spins to be gentler on fabrics. As the spin progresses, less and less water is expelled. At first, water pours out, but as the fabrics dry, the rate of water removal slows. Eventually, almost no more water is being extracted, and the machine knows it's time to stop. Near the end of the spin cycle, the drum begins to decelerate. It slows down gradually, just as it accelerated gradually. This gentle deceleration prevents clothes from being thrown around as the drum stops. When the drum finally comes to a stop, the spin cycle is complete. The amount of water left in the clothes after spinning is called residual moisture content. This is typically expressed as a percentage of the dry weight of the fabric. After a high-speed spin at 1400 or 1600 revolutions per minute, residual moisture might be as low as 40 or 50%, meaning the wet clothes weigh only about 40 to 50% more than they would when completely dry. After a lower speed spin, residual moisture might be 70 or 80%. The difference is significant. Clothes with less residual moisture dry faster, whether you're hanging them on a line or putting them in a dryer. Extracting water through spinning is much more energy efficient than evaporating water through heat. If you use a dryer, having clothes come out of the washer as dry as possible means the dryer doesn't have to work as hard or as long. This saves electricity and reduces wear on your dryer. Even if you air dry, starting with clothes that are drier means they'll be ready to wear sooner. The spin cycle is the grand finale of the washing process. It's loud and vigorous, a sharp contrast to the earlier phases. But it's also quick, and it's essential. Without it, you'd be taking sopping wet clothes out of the machine, and they'd drip all over your floor. The spin cycle leaves clothes damp but manageable, ready to be dried with minimal effort. And with the spin cycle complete, the washing machine's work is done. The drum stops, the motor turns off. The control panel lights might indicate that the cycle is complete. You can open the door or lift the lid, reach in, and pull out your clean, merely damp clothes. They're ready for the next step, whatever that might be. Hanging them to dry, tossing them in the dryer, folding them and putting them away. But before we finish our journey through the washing machine, there are a few more components we should explore. Because all of this, all the filling and washing and rinsing and spinning, is managed by systems that coordinate everything, making sure each step happens at the right time in the right sequence. These are the control systems, the brains of the machine. We've talked about water coming into the machine, being used for washing and rinsing, and being expelled during spinning. But we haven't yet explored in detail how water leaves the machine, how it's pumped away and sent into your home's plumbing. The drainage system is crucial. Without it, water would accumulate in the machine, and there would be no way to remove dirty water and replace it with clean rinse water. At the bottom of the outer tub, there's a drain opening. This is where water collects after draining from the inner drum, or after being flung out during spinning. All water, whether it's dirty wash water or cleaner rinse water, eventually makes its way to this lowest point. From there, it must be pumped out of the machine. The pump that does this is called the drain pump. It's a small electric pump, typically a centrifugal pump, mounted somewhere near the bottom of the machine. A hose or pipe connects the bottom of the outer tub to the pump inlet. When the pump runs, it creates suction at its inlet, pulling water from the tub. The water flows through the pump and out through the pump's outlet into a drain hose that leads to your home's plumbing. The drain pump is activated by the washing machine's control system at specific times. After the wash cycle, when it's time to drain the wash water, the control system turns on the pump. Water is pulled out of the tub and sent down the drain. After each rinse, the pump runs again. And if there's any water left in the tub at the end of a cycle, the pump will run one more time to ensure everything is drained. The pump must work against some resistance. Water has weight, and it has to be lifted up through the drain hose to reach the drain standpipe or laundry sink where the hose terminates. Most washing machines can pump water up to a height of several feet, enough to reach a typical household drain. The pump is powerful enough to overcome this resistance and move water at a reasonable flow rate, typically several gallons per minute. Inside the pump is an impeller, a small rotor with curved vanes. As the pump motor spins the impeller, the vanes push water outward from the center of the impeller toward the edges, where it exits through the outlet port. The impeller's rotation creates the pressure difference that drives water through the system. Drain pumps are designed to handle dirty water. They can pass small particles without clogging, but larger debris like lint, buttons, coins, or other small objects that might make their way into the wash water can cause problems. That's why many washing machines have a drain filter. This filter is located somewhere in the drainage system, often right before the drain pump or integrated into the pump housing. The filter catches large debris, preventing it from entering the pump where it could jam the impeller or damage the pump motor. Over time, this filter can accumulate lint and other material, and it might need to be cleaned. In front-loading machines, the filter is often accessible through a small door or panel at the bottom front of the machine. You can open this panel, remove the filter, clean it, and replace it, helping to maintain good drainage performance. Some washing machines don't have a user-accessible filter. They rely on self-cleaning designs or on the pump's ability to pass debris. But even these machines can benefit from occasional maintenance to prevent build-up that might slow drainage or cause clogs. The drain hose is typically made of corrugated or smooth plastic, flexible enough to be routed from the back of the washing machine to the drain. It needs to be positioned correctly. If it's pushed too far down into the drain standpipe, it can create a siphon effect, causing water to drain from the machine continuously, even when the pump isn't running. If it's not inserted far enough, or if it's left hanging freely, water might not drain properly, or it might splash back into the room. Most installation instructions specify a height range for the drain hose's end. Typically, the hose should terminate at a height that's higher than the water level in the washing machine's tub, but not so high that the pump can't push water up to that height. This ensures proper drainage without siphoning. During drainage, you can often hear the pump running. It makes a humming or whirring sound, and you might hear water rushing through the hose. If the pump is working hard or if there's an obstruction, it might sound strained. Unusual noises during draining can indicate a problem, Perhaps a clog forming or a pump that's starting to wear out. The drain pump runs for as long as it takes to empty the tub, usually just a minute or two. Once the water level drops below the drain opening, there's no more water to pump. The pump might continue running briefly, but it's just moving air at that point. Then the control system turns off the pump, and the drainage phase is complete. Efficient drainage is important for the overall cycle time. If the pump is slow, or if there's a restriction in the drain path, it takes longer to empty the tub, and the whole cycle takes longer. Keeping the drain filter clean and ensuring the drain hose is properly installed helps maintain good drainage performance. And once the tub is empty, once all the water has been pumped away, the machine can move on to the next step, more rinsing or spinning, or if the cycle is complete, simply stopping and waiting for you to unload the clean clothes. Every washing machine has a control system. This system is what manages the cycle, turning components on and off at the right times, in the right sequence. It's the brain of the machine, making decisions based on the cycle you've selected and the conditions it detects through sensors. In older washing machines, the control system was a mechanical, built around a timer. This timer was a motor-driven device with a series of cams and switches. As the timer motor slowly rotated the cams would press on switches, turning them on or off. Each switch controlled a different component: the water inlet valves, the motor, the drain pump, the heating element. By carefully shaping the cams, engineers could create a sequence of events that constituted a complete wash cycle. These mechanical timers were simple and robust. They had few electronic components, so they were less prone to failure from electrical issues, but they were also inflexible. The cycle was fixed, determined by the shape of the cams. You couldn't easily modify it or add new features. And if something went wrong, if a cam was worn or a switch failed, the whole timer might need to be replaced. Modern washing machines use electronic control systems. At the heart of these systems is a microcontroller, a small computer chip programmed with all the logic needed to run the machine. This microcontroller monitors inputs from various sensors: water level sensors, temperature sensors, door lock sensors, load balance sensors. Based on these inputs and the cycle you've selected using the control panel, the microcontroller decides which components to turn on, when to turn them on, and for how long. Electronic controls offer enormous flexibility. A single microcontroller can manage dozens of different cycles, each with its own pattern of fills, washes, rinses, and spins. You can have a delicate cycle that uses low agitation and low spin speeds, a heavy-duty cycle that uses hot water, vigorous agitation, and high-speed spinning, an eco cycle that uses minimal water and low temperatures, a quick cycle that completes in just 15 or 20 minutes by skipping extra rinses. All of these cycles are just different programs running on the same hardware. The control panel is how you communicate with the machine. You turn a dial or press buttons to select the cycle, adjust settings like water temperature or spin speed, and start the machine. The control panel might have a simple mechanical dial with detents for each cycle, or it might be entirely electronic with a digital display showing your selections and the estimated time remaining. When you press the Start button, the microcontroller begins executing the selected program. It starts by opening the water inlet valves, filling the drum. It monitors the water level sensor, watching for the water to reach the correct level. Once the level is reached, it closes the inlet valves and waits for the soak period. Then it turns on the motor, starting agitation. It runs the motor for the programmed duration, then stops it. It opens the drain valve or starts the drain pump, draining the wash water. And so on, through rinses and spins, until the cycle is complete. Sensors provide crucial information. A water level sensor tells the control system how much water is in the tub. This might be a pressure sensor that detects the air pressure in a tube connected to the tub, which changes as water level changes. Or it might be a float switch that rises with the water level. Either way, it gives the control system feedback about filling. A temperature sensor monitors water temperature. This might be a thermistor, a type of resistor whose resistance varies with temperature. The microcontroller measures this resistance and calculates the temperature. If the temperature isn't where it should be, the microcontroller can turn on the heating element or adjust the mix of hot and cold water being added. A door lock sensor ensures the door is properly closed before the cycle starts. In front-loading machines especially, it's critical that the door is locked during operation. If the door were to open during a spin cycle, water could pour out, or clothes could be thrown from the drum. The door lock engages when you start a cycle, physically locking the door shut. The control system checks the lock sensor before allowing the cycle to proceed. If the door isn't locked, the machine won't start, or it will pause until the door is properly closed and locked. Load balance sensors or algorithms detect whether the load is evenly distributed in the drum. If the load is unbalanced, the control system might pause the spin cycle and attempt to redistribute the load by rotating the drum slowly back and forth. If it can't achieve balance, it might reduce the spin speed or alert you to the problem. Some advanced washing machines have additional sensors. Weight sensors in the suspension system might detect the weight of the load, allowing the machine to adjust water level and detergent dosage automatically. Optical sensors might detect the turbidity of the water, indicating how dirty it is, and adjust the number of rinses based on that. Touch sensors on the control panel replace mechanical buttons, providing a sleek interface and additional flexibility in display options. The control system also manages safety features. It ensures that the heating element doesn't overheat. It monitors for leaks, and if a leak is detected, it can shut off the water inlet valves and activate the drain pump to empty the tub. It prevents the door from being opened during operation. It can detect excessive vibration or abnormal sounds and stop the machine if something seems wrong. All of this happens automatically without your intervention. Once you select a cycle and press start, the control system takes over. You can walk away, and the machine will do its work, following the programmed sequence, adapting to conditions it detects through sensors, and stopping when the cycle is complete. Electronic control systems have made washing machines more capable and more efficient. They've enabled features like automatic dispensing, where the machine measures out detergent for each load. They've enabled smart features, where the machine can connect to your home network and be controlled from a smartphone app or integrated with other smart home devices. You can get notifications when a cycle is complete. You can start a cycle remotely. You can download new cycle programs or receive firmware updates that improve performance. But at their core, all control systems, whether mechanical or electronic, serve the same purpose. They orchestrate the sequence of events that makes up a wash cycle. Fill, wash, drain, rinse, drain, spin. Over and over, reliably, every time you do a load of laundry. The control system is what makes it all happen, silently managing the symphony of components that transform your dirty clothes into clean ones. And so we come to the end of our journey through the washing machine. We've explored every major component, understood every phase of the cycle, examined the physics and chemistry that make cleaning possible. From the moment water enters through the inlet valves, through the mixing with detergent and the agitation of clothes, past the rinsing and the final high-speed spin, we've followed the complete process from start to finish. It's a remarkable system when you really think about it. A washing machine is a carefully orchestrated collection of mechanical, electrical, and chemical processes, all working together toward a single goal: clean clothes. The engineering that goes into a washing machine is sophisticated, refined over decades of development, tested in millions of homes, constantly improved to make washing more effective, more efficient, more convenient. And yet it all seems so simple from the outside. You put dirty clothes in, you add detergent, you press a button, and an hour later you have clean clothes. The machine hides all the complexity, all the careful coordination of water flows and motor speeds and cycle timing. It just works, reliably, predictably, day after day, load after load. Think about what happens inside that machine. Water flows in at precisely controlled rates and temperatures. Detergent dissolves, and its molecules begin their molecular work, surrounding oils and grease, breaking down stains. The drum or agitator creates motion, rubbing fabric against fabric, working the detergent through every fiber. Water is drained and replaced, rinsing away dirt and soap. The drum spins at hundreds or thousands of rotations per minute, extracting water through centrifugal force. Sensors monitor everything, control systems coordinate everything, safety systems protect everything. And through it all, your clothes are being cleaned. Gently but thoroughly, efficiently but effectively. It's a process that once required hours of manual labor, scrubbing and wringing and rinsing by hand. Now it happens automatically, while you do other things, while you sleep or work or relax. The washing machine sitting in your home, that familiar appliance you use perhaps several times a week, is a testament to human ingenuity. It's the culmination of countless innovations, from the first mechanical washing devices in the early 1800s to the sophisticated computer-controlled machines of today. Each generation of engineers has added something, improved something, refined the design a little more. And now, as you drift toward sleep, you can appreciate the washing machine in a new way. You understand what it does and how it does it. You know about the valves that control water, the heating elements that warm it, the detergent that chemically binds to dirt. You know about the drum that holds everything, the motor that drives it, the pump that drains away dirty water. You know about the cycles and the spins and the sensors and the control systems. The next time you do laundry, perhaps you'll think about all of this. Perhaps you'll hear the water filling and know exactly where it's coming from and where it's going. Perhaps you'll hear the drum turning and understand the forces at work, the chemistry happening, the dirt being lifted away. Perhaps you'll appreciate, just for a moment, the quiet brilliance of this everyday machine. But for now, you can rest. Your mind has wandered through the inner workings of washing machines, exploring mechanisms and understanding processes. And in that gentle exploration, in the steady rhythm of explanation, perhaps you've found the calm you were seeking. Perhaps your thoughts have slowed, your breathing has deepened, your body has relaxed into comfort. The washing machine washes, the world turns, and you, safely surrounded by warmth and quiet, can let go now. Let your mind drift. Let sleep come gently, softly, naturally. There's nothing more you need to think about, nothing more you need to understand. Just rest now. Just sleep. If you happen to still be awake, if these explorations have helped you unwind, consider returning to this channel another night. There are more stories to tell, more systems to explore, more everyday mysteries to unravel. But for tonight, this is enough. You've learned, you've listened, and now you can sleep. Sweet dreams,